All right, so today we're talking about a limit. So limits are based on the fact that we have to get a value for a function. If input goes in, we want output to come out. But sometimes it's just not quite that simple. So f of x is our function, and there has to be a single number that we can get close to, called L the limit, as x approaches some other number from either side. When I say either side, I mean either right or left. Positive right, negative is left. Okay, so the limit is L, and this is the notation right there. The limit as x approaches c of f of x equals L. So we kind of went through the first part of this, I think. So I'm just going to go through the second part. So let me scroll down here. All right, so let's basically go from left to right. There's a lot of limits on this page. Let me explain them all. So if you start from the very far left-hand side, where this function goes off and you can't see it anymore, this is g of x, by the way. So g of x on the left-hand side, and we have an asymptote, by the way, right there when x is negative 1. So we'll remember that. All right, so the limit as x approaches negative infinity. This is the only time we really mess with infinity. If you go to the left, you don't stop. It's going up, so we have positive infinity for the limit here. As x approaches positive infinity, look at the right side of the function right there. Then we see that the graph is going down, so we would say it goes towards negative infinity, right? Infinity is basically boundless. There is no bound, so it either goes infinitely up or down. All right, let's go ahead and start at the left side of this. There's a lot of discontinuities going on in this graph. So as we approach negative 3 for x from the left side, there's a hole right there at negative 3. So the function is not really defined at negative 3. However, if you look at approaching negative 3, a limit from the left side, see where there's a negative sign, so that's called a left-hand limit, or LHL for short, LHL, left-hand limit. Then it approaches the value that the function has where that hole is. So if I kind of go straight across here, it looks like it's like, what, negative 0.8, I believe? Yeah, that works. So we'll say it's negative 0.8 is the limit as you approach negative 3 from the left-hand side. Now we'll look at the right-hand side. As you approach negative 3 from the right-hand side, RHL, right-hand limit, you'll see that the graph is approaching. I don't care where it gets to, okay? It gets to the same place it's approaching. In this case, it's positive 0.7. So I want you to notice that those two limits are not equal. There's that big gap in between them, okay? So that creates a discontinuity in a situation where the limit does not exist. DNE, if the left-hand limit does not equal the right-hand limit, there is no overall limit for the function at negative 3, okay? They have to be equal in order for them to have a limit. All right, next, let's look at the next part of the function. So basically the graph kind of cruises down here to negative 2 for x. So when the x value is negative 2, the limit as you approach negative 2 on the left-hand side, the LHL left-hand limit, is going to be 0. The right-hand limit as you approach negative 2 from the positive side is going to also be 0. And therefore, since those are equal and they both are values, they're actual numbers, they're not infinite, we would say that the limit is 0. It does exist because the right-hand limit and the left-hand limit are equal. All right, so continue moving from left to right along this function. Then you're going to see that we're going to approach an asymptote, right, at negative 1. Now, asymptotes are unusual things for discontinuities because if you approach on the left-hand side, it's unbounded. It goes right up straight towards infinity. And if you approach from the right-hand side, the right-hand limit of negative 1, it's also infinity. So at first you might think, oh, those are equal, so it is infinity, but that's not true, okay? Infinity is not a value, so unless you're going towards infinity, you can't use infinity. So in this case, the limit does not exist. Okay, you can do that, negative infinity, but right-hand limit and left-hand limit are not values that you can define as being equal. Infinity doesn't count. So we'd say it does not exist, and the reason it does not exist is because it's unbounded, okay? So anywhere in the middle of the function, if it's unbounded, we would say the limit does not exist. It's not a value. Limits are all about getting numbers that you can use to solve real problems, okay, eventually. And okay, so moving on. As you approach 0, when x is 0, from the left-hand side, let's say that's negative 0.6 right there. From the right-hand side, it's also negative 0.6. Therefore, since the left-hand and right-hand limits are equal, the limit as g of x, or x approaches 0, g of x is negative 0.6. Continuing on, the last piece there. So now the next place we're going to stop is at x equals 2. So if you follow the graph to the place where x equals 2, from the left-hand side, okay, as you approach 2, you cannot get to 2. There's a hole there, at least for that point, the open circle. We're going to say that's negative 0.5 on the left-hand side. On the right-hand side, it approaches, okay, the value you approach is going to be also negative 0.5. So the limit as x approaches 2 for this function is actually going to be negative 0.5. Now notice that that's not the value. The negative 0.5 is the limit as you approach 2. It's not actually the value you get out of the function when you put in 2 for x. Okay, so f of 2, or g of 2, I'm sorry, g of 2 is actually equal to something else. I think that's negative 1. All right, so kind of keep that in mind. So the function is defined at negative 2. Sorry, f of x is not right. It's g of x. So the function g of negative 2 is defined, right? And that equals negative 1. But that's not the same as the limit as you approach, okay? And that's because that point is kind of down to the side. And that's okay, that happens. That's not something we worry about. Okay, so let's talk about, so if a limit exists, it means that the left-hand limit and the right-hand limit are equal. So what this says is if you left-hand limit, right-hand limit are equal, then you have a limit for a particular x value and a function. So if you get closer and closer to a number, the y value, from both sides, okay, then there is a limit. All right, so let's talk about when you have discontinuities. So there's basically 6 different options here on the right side of your screen, right? A, B, C, D, E. E is the only one that's continuous, and then F. So these are different types of discontinuities. Look at A, there's a hole there. So you definitely have to pick up your pencil. Look at C. So all of these are, if you were going across your paper, you'd have to definitely pick up your pencil. And then F, there's an asymptote, which is like a wall. You definitely can't just draw over it, okay? So look at these 3 requirements up here, 1, 2, and 3. First of all, up at the top there, a function is continuous when, number 1, f of c is defined. So it's got to be defined at a point, okay? The limit exists, right? So being defined at a point means that you have a dot that you don't cross over, right? So look at A. A fails that number 1 up at the top. When I say number 1, I mean, is f of a value defined? No for A, no for B. That's an open circle, right? Now for C, it passes because there is a dot. There is a defined point. For D, it passes because there is a dot. And for E, it passes. So it passes the fact that there is a defined point. It fails, that for the F, that should say fail. I'll fix that here in just a minute. Number 2 is the limit. Does the limit exist? Okay. And then 3 is the limit equal the defined point. So let's look if the limit exists. So number 2, does the left-hand limit equal the right-hand limit? No, not for A. So you approach from the left and right, they're different. B, you're good. Okay. The left-hand and right-hand limits approach the same place. For C, no, you fail. Number 2, the left-hand and right-hand limit are going to be different, so their limit does not exist. And then for D, you pass. You approach the same place for a limit. And then, of course, for E, you pass because it is continuous. And then for F, we're going to fail. That should say fail number 1 and fail number 2, okay? Because if you approach from the left or the right, you're going to approach infinity, which is unbounded. Okay, so now let's go back. Now, is the limit equal to the defined value? Are 1 and 2 equal, basically? So for A, you're definitely saying no, because if a limit doesn't exist, it can't equal anything, right? For B, we're going to say no, it fails. For C, we're going to say no, it fails. For D, so basically, in order to be continuous, a function, it has to pass 1, 2, and 3 at a specific point, let's say, okay? So basically, the only one that's a function would be part E. Okay, so let's talk about the different ways you can be discontinuous, right? A discontinuity is either removable or not, right? If you can simply plug up the hole and just keep going along the function, we'd say it's removable. Like look at B right there. The hole is actually in line with the rest of the function, right? It's non-removable if there's no way that you can just fill in the hole, right? If there's a gap. So look at A. A is non-removable because there's that jump or that gap in between the place where the hole is. Same goes with C. D is removable because if the function picks up on the other side where it left off. And then an asymptote is definitely non-removable. You can't just skip over an asymptote. So functions that do not have asymptotes, polynomial functions, root functions, exponentials, logarithms, over their domain, they do not have asymptotes. They do not have discontinuities. Rational functions do. Asymptotes or holes, I'll talk about that in a minute. And then tangent, cotangent, secant, cosecant, their discontinuities are asymptotes, so they are non-removable. If it's a piecewise function, if it's got 2 pieces, then you can kind of imagine that it would be have a discontinuity that's either removable or not removable. And then step functions being an example of that. Okay, so let's take a look at if you have a rational function, You should algebraically, in other words, no graph should be required to figure this out. Now, we'll graph these, calculator or Desmos, as a tool to understand. So look at the bottom of this function. When would that equal 0? So in order to figure that out, we have to do all the factoring that can be factored. So the top is x minus 1 times x minus 4. The bottom is x plus 2 times x plus 3. And now the bottom is what creates the discontinuities, right? So if x is equal to negative 2, that would be a discontinuity. And if x is equal to negative 3, we would have another discontinuity. Now those would be non-removable, and they would both be asymptotes. Okay, so let's look at the graph, and I'll show you why. And the reason they're non-removable is because they're still there. There will be situations where you actually cancel them out or they go away. So let me show you the graph here. So if we graph this, I already set this up for you. So we'll graph the function without factoring it. You want to graph it in its original form. Whoops, let me fix that. Turn the graph on there, zoom 6, get a standard window, and there it is. So if you look at that graph, you can look at the place where x is negative 2 and negative 3, and the graph clearly is approaching infinity, or it's unbounded at those particular spots. So there's like negative 3 right there, and then, that would actually be the negative 2 asymptote, and then negative 3 would be the one over there, okay? Now there is more to this function, okay? In between negative 2 and negative 3, there are going to be places where the graph actually does exist, and it's going to be like a little kind of a loop at the bottom, okay? So let me change the graph here. You can go between negative 2 and negative 3, you just can't get to negative 2 and negative 3 themselves. Let me change the window here and try to go all the way down. Whoops, that's the wrong way. Let me go all the way, let me go all the way down. So if I go all the way down, sorry, it took me a minute there, negative 300. So you can kind of see there's that little piece of the graph between negative 2 and negative 3. So it does exist, okay? Feel free to pause or slow this down if you need to. I know it's going pretty quick. I just want to make sure we get through it. Okay, number 2. 1 and 2 are the same. They're both rational functions. But if you look at number 2 here, this example, if you factor the top, you're going to get x plus 4 times x minus 1. And the bottom is x plus 4 times x minus 4. It's difference of squares. Now notice that the two factors, top and bottom, cancel out, right? It creates a 1. That's what we mean by removable, right? You just removed a factor. So you end up with x minus 1 over x minus 4. Now the graph will show two discontinuities. One where x is 4, that was not removed, therefore it's an asymptote. The other discontinuity is the factor on the bottom that canceled out. So x equals negative 4 is going to be a removable discontinuity, and that's a hole. Now holes are strange because they're hidden. You would never know they're there unless you know that you're supposed to be looking for them. And that's why they're removable. So let me go to Desmos to show you this. So don't count on using Desmos for every problem, but I do want you to be able to get the concept down, right? So here's the graph I was just talking about. So you can clearly see that x equals 4. Look at x equals 4, and you definitely see an asymptote. Now, go to where x is equal to negative 4, and you're going to see right there, right? It's kind of hidden, but right there, wait, there it is, right? Negative 4, there's a hole, but it's really, really hidden. So you do have to go there to know that it's going to happen. But of course, algebraically, we knew it would happen because we canceled it out, and that's removable. Okay, moving on. Let's do 2 more that are going to look a lot like those first 2. So x plus 3x minus 3, and then x plus 3 on the bottom. We're going to remove x plus 3. So this function is just going to be a line, x minus 3. The discontinuity will be negative 3, and it is removable, therefore it's a hole. And this would just look like a line with a hole in it, basically, at the place where x is negative 3, right? So if you wanted to graph this, it would look something like this, right? Negative 3 y-intercept, the slope is 1. And if you go to where x is negative 3, you'd see a hole right there, and then the graph would keep going, right? You wouldn't actually see the hole, but if you looked for it, you could find it, but it is very hidden. That's why it's removable. For 4, to factor the top, we're going to group it. We're going to factor x squared out and get x plus 5. The second 2 terms, we're going to get negative 9 and x plus 5. I'll help you with the factoring a little bit if you need that. Then we'll factor the x plus 5 out, and we have x squared minus 9. I'm just doing the top first. So it's x plus 5 times x plus 3 times x minus 3 all over. Now let's factor the bottom. That's just going to be x plus 3, x plus 5, and x minus 3. I'm sorry. And you'll notice you cancel out or you remove 2 factors. So you're going to have 2 discontinuities. The simplified function is just a line, x plus 3. So it's going to look a lot like a line. Actually, it will look exactly like a line. But you'll have discontinuities where x is negative 5 and x is 3. And they're both removable. Therefore, they're both holes. Okay, now let's talk about trig functions. Sine and cosine, if you graph sine and cosine, There's nothing about them that would create discontinuity. There's no values that would create an undefined or an asymptote type of situation. So sine and cosine will have no discontinuities whatsoever, but all the other trig functions will. Tangent, cotangent, secant, cosecant, okay? So we're gonna focus on those ones, right? Now the graph, again, will help you. Desmos will be a great tool. A graphing calculator will also help as you go through that. So tangent and secant are pi over 2 plus pi k. So when you look at tangent, look at what's going into it, right? Tangent of, in this case, pi x over 8. So this is going to be non-removable. It will be an asymptote, or asymptotes, I should say. And when will that happen? That's going to happen when what goes in, which is what? Pi x over 8. Okay, hold on. So when you graph this here, there's that function. So look at what it looks like. See those waves? What happens between those waves? Okay, at looks like what, -4 around that spot, around -4, around +4, you're going to see vertical asymptotes, right? So where do those asymptotes show up, right? So those asymptotes are going to show up. Let me draw a little picture of that. So just so you know, right? They just continue over and over again. It's infinite along the way, right? And the asymptotes would go straight down like that and like that. And they would keep going infinitely to the left and right. So these asymptotes are going to happen when you try to put in a value that's undefined. So take pi x over 8 and figure out what x value would make that equal, go back up here, the undefined, right? Pi over 2 plus pi k. This is what you did when you guys did your review that first week, right? Pi over 2 plus pi k. So now we're going to solve for x, right? So we're going to multiply by 8 over pi, and then we'll simplify everything out and get x all by itself, okay? So I'm going to multiply by 8 on top, pi on the bottom, both sides, x by itself on the right, or on the left, I mean, and 8 over pi on the right. So we'll distribute that, and you would get what? 8 pi over 2 pi plus pi k, 8 pi k over pi. Cancel out the 8, 2, that's a 4, and then that's going to be simply 8k. So there you go. So any value of x that's either 4 or 8, multiples of 8 plus 4, or minus 8, either way, should work, right? So if I did, let's say x equals just 4, 4 plus 8 once, then you'll get an asymptote right there, as we knew we would. So x equals 12. Let's see, let's do 4 plus, let's do -8. So your times 8 times -1, plus 8 times -1, I should say. And there would be your asymptote. Let's do -4. There's an asymptote. And we'll try one more, right? 4 minus 2 8s. So that would be 16, right? -16. So there you go. Feel free to pause and go back and look at that. Okay, now cotangent. So look at cotangent. Cotangent is going to be like cosecant. So pi k is where you have an asymptote, right? Look at what's going into the cotangent. Let's try to do this one without graphing it. Let's just think about, so it's going to be non-removable because all cotangents have non-removable asymptotes. Not going to have any holes or anything like that. And so look at what's going in and set it equal to pi k. So we'll do 1/2 x plus 3 pi equals pi k. And then we're going to solve that for x and figure out what the values are for the asymptotes, the non-removable discontinuity. So step 1, I'm going to subtract 3 pi from both sides. Cancel that out. So I have pi k minus 3 pi on the right, and then I have 1/2 x on the left. Now, multiply by 2 on both sides, and I get x equals 2 pi k minus 6 pi. And you can rewrite that. You can put the minus 6 pi first, and you could do plus 2 pi k after that. It really doesn't matter, but usually the k is the thing you want to put at the end, right? So if you wanted to graph that, you could find asymptotes at each of those particular x values, okay? Let's keep going. Secant. So if you look at a secant graph, okay, I'm sorry, let me go back here. So let's go ahead and look at that one. Cotangent, there it is. Let me clean this up just a little bit. Go up, turn that one off. Okay, so look at the cotangent. Let me zoom it a little bit better. Whoa, there we go. Okay, so if I were to graph what? X equals -6 pi plus 2k. Sorry, -6 pi plus 2 pi k. -6 pi plus 2 pi k, and I'm not going to be able to do k on here, so I'll just do this. I should see there. So that looks like the correct asymptote, right? And you can change those values, -6 pi plus, let's do like 2 pi times 2, and you're going to see that that also would create an asymptote right there. So we could get every single asymptote, but of course there's an infinite number of them. That's why we have k to make sure we know where they are if we need to find one. Okay, let's go ahead and move on. Secant. Secant is going to behave just like tangent. So we're going to do pi over 2 plus, we're going to set what's inside equal to where the discontinuities are. So non-removable, and it also is a asymptote. And cosecant, by the way, is the same thing, so I might as well just copy that over there. So we're going to find asymptotes for both of these, right? Okay, so let's take 3x minus pi over 4 and set it equal to where the secant has its asymptotes. You cannot put in a value that would be pi over 2 plus pi k. K would be just any integer, right? So let's solve for x, right? Let's add pi over 4 to both sides. There we go. Cross that out, and then pi over 2 plus pi over 4. Let's change pi over 2 to what? Let's do 4 pi, wait a minute, that would be 2 pi over 4, right? 2 pi over 4 is the same as pi over 2, so that would be what? 2 plus 1, 3 pi over 4 plus pi k. And then let's divide everything by 3 or multiply by 1/3. And you get x is equal to, and that would be 3 pi over 12 plus pi k over 3. And then we can reduce our fraction here. So 3 over 12 ends up being what? Just 1/4, okay? So we'll clean that up, and it would be just pi over 4 plus pi k over 3. So that last one, number 9, I got to fix that. You can reduce 3/12. Okay, so here I'm going to set 3 over 2 x equals pi k, and it's pretty simple. You just multiply by 2/3 to solve for that. Okay, let's move on. So if I give you a piecewise function, right, you want to be able to create a continuous function, right? So as this function is right now, the value of a means that it may not be continuous, okay? So think about this graph, right? This is a parabola, x squared minus 88, and you only graph it when x is less than 11. So it's a parabola shifted 88 down, and there's a hole, an open circle when x is 11 right there, and the rest of the parabola is there. Now, 11 goes in, something would have to come out to fill that hole if we're going to make it continuous. Now, the only way to fill it is to use AX, right? AX is a line, and we'll do that in blue. And that line is going to be graphed when x is greater than or equal to 11. So imagine a line that goes through 0, 0. We got to figure out the slope of that line, not the one above or below, but the one right there in the middle that connects to that open circle, so you don't have to pick up your pencil to draw this. So we need to get the output that's required. So what is x squared minus 88? What's the, if you were to put 11 in for x, right? So 11 squared minus 88, and we'll get the place where that hole is, right? 11 what? So that should equal 33. If you put in 11, you get 33 back for y. So we want to figure out what would give us 33 back out for that function, right? So a of 11 is equal to 33. So if you want to get 33 out, you would have to put a 3 in. So if a is 3, that would work. And here I'll show you what this looks like on Desmos just so you can get the idea. Again, this is just for the concept, right? So there's my parabola. It's undefined at 11. The line, if a is any of these numbers, it's not working. But when you go to 3, there it is. Perfect, right? So you basically plug the hole where the undefined point was, and now you have a defined point, and you have a continuous function, right? So that should work. You fix the discontinuity. Okay, let's try one that's a little bit more complicated. This one is a line. It's actually 3 lines, right? So we're going to graph, first of all, y equals -2, and we're trying to find values for a and b that would make this continuous. So in red, we'll graph y is -2. Blue, we'll graph ax minus b. And for green, we'll do y equals 7, right? So here we go. So go to where x is -3, and draw the line where y equals -2, okay, and put a dot, and that's what we mean by the first line there. Y is equal to -2 is that line. Okay, now let's go ahead and do the green. Y is equal to 7, and we only graph that when x is greater than or equal to 3, like that. So we kind of need to bridge the gap between those two functions, and we need to find an a and a b that would do that for the blue function, right? So it's going to have to connect those dots just like that, all right? And that's the function that would connect them between -3 and 3. So we have to figure out what values of a and b would go in. So we're going to say -3 goes in. What would come out for the red function? Well, the red function is pretty simple. It's a horizontal line. So it's -2 for y every single time. And the green function, you want to get a 7. So we got to figure out how to graph a line using a and b, ax minus b, so that when you put a -3 in, you get -2. And if you put a 3 in, you get 7. So that's a system of equations, right? And you can solve systems in lots of different ways, whatever's simplest for you. I will use substitution, okay? So if you were to take substitution and you use, let's use this first equation, right? -3a, I'll move the b to the right, the 2 to the left. So that's a value, a way you can substitute for b. So take the second equation, which is 3a minus b, but replace b with negative 3a plus 2, and it equals 7. 3a plus 3a, 6a, minus 2 equals 7. 6a equals 9, therefore a is 9/6. Then we'll reduce that to be 3 over 2. So once you get a is 3 over 2, 1.5 you could say, then you can plug in a and get b. So we'll do 3 over 2 times 3 minus b equals 7. And 3 over 2, it's 9 over 2. Okay, that's 9 over 2, so we'll multiply, or subtract, I'm sorry. Let's say b, when it's by itself, is the same as 9 over 2 minus 7, okay, which is 14 over 2, of course. So 9 minus 14 would give us negative 5 over 2, and that's the value of b. You could also say it's negative 2.5 if you want. So those are the two values for a and b that would work, right? You could graph this, okay, and you would see that at work. I'll do that one real quick with Desmos as well. So here we go. So if a and b, right now it doesn't work, but if you were to connect them right there, almost, move that A, move that B, and B almost there. Okay, you can see how it doesn't work, and you could connect on one side but not the other. You got to kind of play around with both of them, and it looks like that. There we go. So A is 1.5, and that's 3 over 2. B is negative 2.5, and of course that makes the function continuous. Connect the dots is basically what you did there algebraically. Okay, moving on. Okay, let's look at this. So without graphing, we're going to take a look at a piecewise function, right? So this piecewise function, let's say f is negative 1. So that means that at all these different pieces, these different intervals of the domain of this function, let's say negative 1. So if you put negative 1 in to the function, what would you get? Does it exist? The answer is yes, because right there you can put negative 1 in at the place where it would go, and you would get 1 squared minus 2, which means negative 1. So we'll say yes for A. F of negative 1 does exist, and it does equal negative 1. Does the limit on the right side for negative 1 exist? So if you approach negative 1 from the right-hand limit, it would exist, right? Because it's just a parabola. There's nothing about that that would create discontinuity, so we'd say yes, okay? And since negative 1 is the endpoint, we don't have to worry about the left-hand limit if we graph this. So it does. The answer is yes, and it does equal negative 1, okay? Does the limit on the right equal, okay, the value of the function at that point? So the answer is yes. So the right-hand limit is negative 1, the value is negative 1. Are those things equal? Yes, they are. Therefore, we'd say at that particular place where x is negative 1, the function is continuous, right? That's kind of what the part D is kind of saying. Do your answers to A and B, do your answers to A, B, and C basically all turn out to be the same, okay? All right, let's look at this one. This is more of a graph situation, okay? So look at 0, right? There's a discontinuity there, right? So we can, why is it discontinuous? If you go to 0, there's no place that you can go to get a value. It doesn't exist. F of 0 is not defined, it's just a hole. Does the limit exist? No, because on the left and right, it goes to two different places. The left-hand limit does not equal the right-hand limit. So therefore, does the limit equal the value? No, because there's no such thing. It does not exist, so it's not continuous. So that's what it looks like when it's discontinuous, but that's why. And then let's look at 1. Okay, at 1, there is a value. If you plug in 1, you would get 4, because there's the dot. The limit exists because on the left-hand side you approach 5, and on the right-hand side you approach 5. So the limit for x approaching 1 would be 5. Do those two things equal each other? The answer is no, they do not. 5 does not equal 4. So therefore, if the limit doesn't equal the value, it's not continuous at x equals negative 1. Okay? So that would be another discontinuity right there, right? That one is removable, but it is still a discontinuity. Okay? All right, let's do the same thing. 2, you can pretty much tell at 2, it's just continuous. So we can go through the limits. So basically the limit on the left equals the limit on the right and equals the value. Look at 3. That's an endpoint. There is no right-hand limit there. So as you approach from the left, first of all, there is no f of 3. It's a hole. As you approach from the left, you would get 3. You can't say that they're equal, so therefore it's not continuous at the point x equals 3. Okay? Sorry, the limit is 2. That's what I mean. As you approach from the left, you would get 2. It's not continuous because those two things are not equal. So to be continuous, that's what has to happen. Okay, finally, intermediate value theorem, otherwise known as the IVT. So basically what this means is that if you have a continuous function on a certain interval from A to B, from a low number to a high number, A to B, and you have another number that's in between the outputs. So you have A there, B there, and there's a high f of A, and there's a low f of B. If you pick a number in between f of A and f of B, right, then you know that there has to be a number C in between, right? This is all about being in between, right? If you're in between the x values, there has to be a value that's in between the y values. That has to work together both ways, right? So look at this function, right? If you know, explain why f of c equals 2, this is a parabola. So if f of c equals 2 for the function below, it has to be true for something on the interval from 0 to 3, okay? So this is just a parabola that opens up, right? So imagine x equals 0 to x equals 3. That's the x interval. So plug in 0 for x. So if x goes from 0 to 3, y would go from -1. And then if you plug in 3, it would go up to 3 squared, that would be 14, right? So as x goes from 0 to 3, y goes from -1 to 14, or f of x goes from -1 to 14, right? Therefore, if you say 0, f of c is 2, that means that's between -1 and 14, right? So therefore, there has to be a value, okay? 2 is between 0 and 3. Therefore, f of 0, okay, has to be between f of 0 and f of 3, okay? So that means that 2 has to be in there, right? You can't get from -1 to 14 without going through the value 2, okay? All right, let's do this again. So think about a function that's cubic, x cubed minus 15x plus 2, and where that function equals 0. Now, to equal 0, a cubic function could just go straight through the x-axis and cross once and equal 0 one time. Or it could cross through twice, 3 times actually, okay? So there's 3 x-intercepts, or it could do a little bouncy thing on the bottom or top and maybe do something like that and be 2 x-intercepts. So when you equal 0, you kind of have to have an idea of what the shape of the graph is looking like there, right? So between -4 and 4, ooh, I can probably fix these graphs. So from -4 to 4 means that, yeah, we'll put the x-axis maybe over there. Maybe, yeah, I'm going to move that over a little bit so it's right there. Okay, yeah, and then we'll do the same thing on the right. So one of these 3 things is true. So we kind of have to keep these graphs in mind, right? So what we're going to do is we're going to say if x goes from -4 to 4, right? Okay, what's the value? We want to see if there's 3 places where you could get 0 out, right? So we're going to figure out what happens when you put -4 into this function, okay? So if you do -4 in, okay, calculate that all out, and then you would get -2, right? So if x is -4, y is -2, and if you put in just 4, you would get 6. So the input goes from -4 to 4, the outputs go from -2 to 6. Well, you can't get from -2 to 6 without passing through what? The answer would be, of course, 0, right? Negative numbers to positive numbers. So there is at least one place, at least one, where the graph equals 0, okay? Now it's going to be one of those graphs right there. So now we can go ahead and graph the function. And we're going to know really, really quickly, by just seeing the shape of it, we're going to know really quickly whether it's there's only 1 or there's 3, okay? Because there's really, and there it is right there, right? So you can clearly see that if x goes from -2 on the left, okay, and there it is right there, you're crossing the x-axis, and then go to 6 on the right, okay? I'm sorry, go to 4 on the right. So if you go from -4 to 4, you clearly cross the x-axis 3 times, right? So there would be an example of what we're talking about, right? So there's -4 all the way to 4. And if you know that the value of x goes from, or the y value goes from -2 to 6, you know you cross the x-axis 3 times. So there's 3 ways to get from -2 to 6. You're going to cross through 0 3 times. Okay? All right. So we'll go through that. If you have any questions, let me know. We'll talk about that a little bit more in class. Slow it down, rewind it, do whichever you have to do. Okay. See you later.